Okay. Mhm, mhm. Okay, so we are going to start again, but I think we are missing someone. Eamon has not joined the group. Okay, yes, she's joined. Great, so we can start. So now we are going to start another topic under the chapter of beta decay. The chapter is the same, which is beta decay, but we are talking about another topic under beta decay. And this is angular momentum and parity selection rules. Okay, so in this case we have two types of decay. Okay, I'm referring to Crane page 289. Okay, so we have allowed decays and we have forbidden decays. Okay, so let's first talk about allowed decays. Okay, so you're familiar with the concept of angular momentum. You remember this?
Yes, ma'am.
Yeah, so we also studied this in chapter number 2. And you can also go and do a small recap from chapter number 2 if you just to revise yourself. Okay, and you remember the concept of parity?
Yes, ma'am.
Yeah, so again, there was a small section on parity in chapter number 2. You can go and look at it there. Don't be frightened for those of you who have not studied quantum mechanics, because we are using just small formulas from there, and whenever we use them, we explain them. ठीक है ना? So it's not that strange. Okay, so just don't be
Okay,
frightened.
ma'am.
समझ आ रही है ना?
Yes, ma'am.
हाँ, डरना नहीं है. डरने, you know, actually डर जो है ना, fear जो है ना, it blocks your mind. So keep your mind open and you will not have a problem, because the word itself is not scary. अभी मैंने छोटी सी बात की थी, like wave particle dualism. This is something I think you've been hearing for about since a long time. It's a very important concept, but that does not mean it's a difficult concept. ठीक है ना? अब तक आपको ये तो समझ आती है ना?
Yes, ma'am.
This is also quantum mechanics. ठीक है ना? और quantum itself, what does the word quantum means?
Discrete.
Okay. For example, like the photon, we just talked about the photon, and the photon is called as a quantum of energy, right? Quantum is a particular value, right? Okay, and the plural is quanta. So basically, it's not that difficult or that complex. Don't be scared. Because yes, we do use a lot of equations when we are doing the derivations and all that, but right now we're not going to go into so much complexity. We're just using the main concepts, and whenever we use a concept, we always explain it. And whenever you need to remind yourself of some little formula or some little terminology, you can always go back to chapter number 2. Okay, and again, chapter number 2, we are not using that 100%. We are only using that a few things from there. Is that clear? ठीक है?
Yes, ma'am.
So never allow fear into your mind. Is that clear? ठीक है ना? You will never.
Yes, ma'am. घबराना नहीं है.
घबराना बिल्कुल नहीं है. समझ आ गई ना? Whenever you give way to fear, then you lose the ability to learn. समझ आ गई है ना? बहुत से बच्चे सीख नहीं पाते just because fear blocks your mind. Okay, so if you're not afraid, you can learn anything you want to learn. ठीक है? Okay, with that we are now going back to the topic of the allowed decays, and in this case, so the electron and neutrino wave functions are replaced with the values at the origin. Okay, so you know what are wave functions? Yeah, you've been studying this, I think, in 104 also, right?
Yes, ma'am.
So the symbol normally we use is psi, and any particle, for example, or any system in physics can be represented by a wave function, because of the concept that we are using, that every particle can also behave as a wave. Okay, so this is not something difficult or strange, and we're not going to go into the complexities. We're just going to make a discussion related to our topic. Okay, so this means that the electron and neutrino have been regarded to be created at r is equal to 0. Now again, you can visualize this, है ना? Whenever we speak of a particle or a wave, we are normally referring to some coordinate system, right? ठीक है ना? And the coordinate system, for example, can be the Cartesian coordinate system, which is in terms of x, y, and z. And we also sometimes use the polar coordinate system or the
R theta.
r theta, right? So in this case, we're using, if we want to take the origin in the polar system, we will take r is equal to 0. So we are assuming that this particle is at the position r is equal to 0. So it's not complex, it's not difficult. Okay? So in this case, they cannot carry any orbital angular momentum. So if they're at the origin, then we can say that in this case, they cannot carry. These are assumptions, approximations, okay? Just to simplify the problem, okay? We always start with the simplest, explanation. That's the reason for this. Okay. Wow. Okay. So the only change in the angular momentum of the nucleus must result from the spins of the electron and neutrino. Okay. So, the only change in the angular momentum of the nucleus must result from the spins of the electron and neutrino. Okay. So each has a value, the electron and the neutrino, each has a value of spin S is equal to half. So these two spins can be parallel. In that case, total S will be equal to 1, or antiparallel, and there we can say that total S is equal to 0. So we are looking at the different cases that are possible. Okay. Achha. So if the spins are antiparallel, now we are going to give them some names. Okay. If the spins are antiparallel, okay, we will call them Fermi decay. You remember Fermi?
Yes, ma'am.
Yes, ma'am.
What do you know about Fermi?
Dr. Enrico Fermi was a great theoretical and applied physicist.
Yeah, he was
He
good
did.
in both theoretical and experimental aspects of nuclear physics. That's great. And he was an Italian, right? And what did he do? Anything you
He died
remember?
of cancer.
Huh?
He died of cancer because he did not care about his own well-being and used to put the cylinders of enriched uranium by his bare hands.
Yeah, he's also famous for the first time to demonstrate the fission process, right? I think he called it the nuclear pile, right? The critical mass required for a fission to start as a part of the Manhattan Project, right? But anyway, he did get a Nobel Prize, and what impresses me is that he was good both theoretically and experimentally. So that's an interesting combination, right? Okay, so then in the allowed approximation, L is equal to 0. Okay, so we are talking about the spins being antiparallel. We are calling this the Fermi decay, and we are using the approximation as we wrote previously, that the angular momentum, orbital angular momentum, L, as you remember from chapter number 2, is the symbol for orbital angular momentum. S is the symbol for spin. And the total angular momentum is a combination of the spin and the orbital angular momentum. So in this case, since we assume that the orbital angular, it's at the origin, the orbital angular momentum L is equal to 0, and the spins are anti-parallel. This is one case, and this is called the Fermi decay. Okay, so in this case, we can say that delta I is equal to I minus IF okay, minus IF, and this should be equal to 0. What is capital I?
Does that note its moment of
Intrinsic
inertia?
angular momentum.
Huh? No,
Does that
in this case, it is not the moment of inertia. Okay. I know in mechanics, when we use I, it is the moment of inertia, but we are not talking about mechanics in this case. We are talking about angular momentum. And again, in this book, according to the symbols that are being used, you can check them. Capital I is the total angular momentum. Okay. So capital I is a sum of the spin angular momentum and the orbital angular momentum. Okay. So S is the spin angular momentum. L is the orbital angular momentum, and their combination, their sum, will give you the total angular momentum, which is capital I. So what this equation represents is that the change in total angular momentum is equal to the difference in the initial angular momentum and the final angular momentum, the total. And this should be equal to 0 in the case of Fermi decay, because in the Fermi decay already L is equal to 0. And also we are assuming that these are anti-parallel, and in the case of anti-parallel, as I just told you a few minutes ago, total S is equal to 0. So if both L and S are equal to 0, then the total angular momentum change is equal to 0. So we are talking about the Fermi decay. Is that clear?
Yes, ma'am.
yes, ma'am.
Good. Okay. Okay. Now we're going to talk about the second case. In this case, we assume that the electron and the neutrino spins are parallel. Okay. So this case is called a Gamow-Taylor decay. Let me write it again. It is called Gamow-Taylor decay. Okay. And in this case, the total angular momentum, they carry a total angular momentum of 1 unit. Okay. So can we just do a small recap right now, so to make sure that you followed? So we are talking about allowed decays, okay? And in allowed decays, we talked about 2 cases, right? So what's the first case?
Fermi decay.
Fermi decay, very good. So in Fermi decay, again, we assume that the orbital angular momentum L is 0 and the spins are anti-parallel. And if the spins are anti-parallel, then S is also equal to 0, and the change in the total angular momentum will be 0. So that was the
0.
first. ठीक है. And then in the second case, we talked about the spins of the two particles, the electron and the neutrino, to be parallel. And then as we said that if the spins are parallel, then total spin is equal to 1. And
1.
yeah, and as we have already made the assumption that L is equal to 0, then the total angular momentum would be also be equal to 1. Is that
1,
clear?
yeah.
ठीक हो
Yes,
गया?
ma'am.
Great. Okay, so let's erase this. Okay. So, therefore, I and IF must be coupled through a vector of length 1. So we can say that I is equal to IF plus 1. You can imagine a vector diagram, and in this case delta I, since it's equal to 1, so we can write this. So this is possible only if delta I is equal to 0 or 1, except for I is equal to 0 and IF is equal to 0, in which case only the Fermi transition can contribute. Okay, right.
Excuse me, ma'am.
The
ये
board, yeah.
vector of length. Can you explain this?
Who can explain this? Who understood it? देखो, angular momentum is a vector. ठीक है ना? ये
Yes,
रामीन
ma'am.
रामीन बोल रही थी ना? Right. So angular momentum is a
Yes, ma'am.
vector. ठीक है? I is a vector. IF is a vector. ठीक है? So according to the addition rule of vectors or subtraction rule of vectors, when the change delta I is equal to II minus IF, तो उसको करोगे तो triangle बनता है ना?
Yes, ma'am.
याद आ गया ना? The simple
ma'am.
basic rule of addition subtraction of vectors. उसमें triangle
Yes,
बनता
ma'am.
है ना? तो if one side is II, the second side is IF, the third side would be delta I. ठीक है ना? And in the first case, delta I was 0. In the second case, delta I was 1.
Right, ma'am.
अब समझ आ गई है ना?
Yes, ma'am.
Good, great. Okay, so if the electron and neutrino carry no orbital angular momentum, then the parities of the initial and final states must be identical. Okay, who can remind us a little bit about parity? Hmm? Parity yaad hai?
Ma'am, it's
Na-
ma'am,
Yes.
it's a reflection of all the coordinates through the origin.
Okay, it can be a reflection of a property, for example, a vector. And if after reflection, you can imagine a mirror concept, okay? If after reflection it remains the same, then this is known as positive parity, okay? Or even parity, right? You remember? And
Yes, ma'am.
if after reflection there's a change, then this is known as negative parity,
Odd parity.
or it's known as odd parity.
Odd parity.
Odd parity.
ठीक है. So you can go and look at this on page 38 in chapter number 2. ठीक है, ज़्यादा complex होने की जरूरत नहीं, बस आपको basic concept आना चाहिए, right? And what is the symbol for parity? You remember the symbol for parity?
Pi.
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 In this book, the symbol for parity is pi, but in some books you also have p, for example, as parity. But in this book, we are using pi. ठीक है? Okay. So you also have a table at the end of the book जहाँ पे you can see the values of the parities for different cases. याद है ना?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Good. So since the parity associated with orbital angular momentum L is minus 1 raised to L. Okay, therefore the selection rules, अच्छा ये मैं दोबारा लिखती हूँ, but remember कि parity का topic is page 38 and this is chapter 2, just in case you need to revise it. Okay, you can always refer back to where we started from, so just to keep it simple. Okay. Oh my god. Okay, so let me write this again. Since the parity associated with orbital angular momentum L is minus 1 raised to L. Okay, therefore the selection rules for allowed beta decay are delta I is equal to 0 and 1, and delta pi, which is a change in parity, is equal to no. No means there's no change in parity. ठीक है? So these are important.
Yes, ma'am.
These rules are very important. Okay. Okay, right. So I would like to end it here, and so next time we will again discuss this with the help of examples. Okay.
Okay, ma'am.
Okay. So take care.
Allah Hafiz, ma'am.
Allah Hafiz.
Bye bye, ma'am.
Bye.
Allah Hafiz.
Allah Hafiz.
Allah Hafiz, ma'am.
Allah Hafiz. Okay, take care.